Now we're going to get into something really cool. Not that the previous sections were not, but this stuff is really exciting, and we're going to get to see some of statistics in action in front of our eyes while we talk about sampling variability and confidence intervals. And we're going to cover a fair amount in this series of 8 mini lectures, including a sampling distribution of a sample mean, and we'll define that. Variability in this sampling distribution, something called standard error. We'll discuss the difference between standard error and what we've been referring to as standard deviation. And then we'll parlay this into creating something called confidence intervals for the population mean mu based on sample information. And then we'll cover the same territory for binary outcomes, which we haven't formally looked at yet, but we will get into in those sections. And we'll look at the sampling distribution of a sample proportion, the standard error for a proportion, and confidence intervals for the true population proportion. So let's kick this off by talking about the random sampling behavior of a sample mean across multiple random samples. When a sample is randomly selected from a population, it is called a random sample. And that may sound tautological, but definitively, by random sampling, we mean in a simple random sample, for example, each individual in the population has an equal chance of being chosen for the sample. So technically speaking, the values in a random sample are representative of the distribution of the values in the population size, regardless of the size of our samples, but they are an imperfect subset. Random sampling helps control systematic bias, selection bias, that sort of bias. But even with random sampling, there's still sampling variability or error, given that our sample does not contain everyone in the population. We're going to get some error in our estimates of that population. And what do I mean by sampling variability technically? Well, think of it this way. If we repeatedly choose samples from the same population of the same size, but we repeatedly take random such samples, and we summarize the sample through a statistic, like a mean, for example, the statistic will take different values in different samples, just because we're not necessarily getting the same elements in each of those samples of the same size. So if the statistic does not change much if you repeated the study over and over again in that manner, you get similar answers each of the time, then it's fairly reliable. There's not a lot of variability from the sampling process. Conversely, if it does change value a lot across repeated samples, then there's a lot of variability in the sampling process. Let's just look at what I mean visually. So recall, we had worked with data on blood pressures using a random sample of 113 men taken from the population of all men. Assume the population distribution was given by the following: a nice normal curve, centered at 125 millimeters of mercury with standard deviation of 14 millimeters of mercury. This is the population, the theoretical population that we generally wouldn't know, but we will for the moment, that we're going to be sampling from and have already shown the results of sampling from previously. Suppose we had all the time in the world. We decide to do an experiment. What we're going to do is we're going to take 500 separate random samples from this population of men, each with 20 subjects. So take a single sample of 20 subjects randomly, then take another sample of 20 subjects randomly, and do this 500 times. And for each of the 500 samples, we will plot the histogram of the sample blood pressure values, record the sample mean, and the sample standard deviation. So here we go. Sample 1, n equals 20. Here's the histogram. And what I've done is superimposed a normal curve over it with the same mean and standard deviation of the sample. And you can see, well, there's only 20 observations here, so it's hard to get a sense of the shape of the distribution at the population level from which the sample came, but it's not that bad of a fit to a normal curve given that there's only 20 observations in it. And the mean here is 125.7 millimeters of mercury, and the sample standard deviation is 10.9. And then in sample 2, we get a different set of values that are also reasonably well approximated by a normal curve, given that there's only 20. And this has a different mean than the previous sample, comes in a little bit lower at 122.6 millimeters of mercury, and the sample standard deviation is higher, 12.7 millimeters of mercury, than with the previous sample. Now, I'm not actually going to take you through the next 498 samples, but you can assume I actually did do that. That's how I spent one of my summers. So at the culmination of this has been done 500 times. So I want to get a sense of how much variation there was in the sample means across those 500 samples. So what I'm going to do now is do another histogram. But in this histogram, we won't find individual blood pressure measurements on individual men, like we did when we were looking at each sample separately. But what we'll find here are 500 summaries, each based on 20 men. In other words, this histogram plots the distribution of 500 sample means based on 500 random samples of 20 men each. And look at that. And I fit a normal curve over that. And that's pretty well described by a normal curve. And let's look at the mean of the sample means. Well, the mean is 125 millimeters of mercury. Does that sound familiar? Hold on to that thought. And let's look at the standard deviation of those sample means. That's equal to 3.3 millimeters of mercury. Certainly smaller than the standard deviation estimates we saw for individual values in the samples we looked at previously. So suppose we had all the time in the world still. So we decide to do another experiment. We're going to take 500 separate random samples from the population of men, this time each with 50 subjects. And so for each of these 500 samples, we will plot a histogram of the sample blood pressure values, record the sample mean, sample standard deviation. Here we go. So let's look at the first two samples I took randomly from that population. Well, now we're starting to see more consistency with that underlying normal distribution in the population from which we're sampling of. And just by having more points, it doesn't change the representativeness of our sample, but we have more data in which to build a picture with, and so it starts to make it slightly clearer. But even so, you can see that these samples yield two different estimates of the sample means and two different estimates for the sample standard deviation. But suppose we did this 500 times, like I said, and in order to get a fix on what's going on with the sample means, we did a histogram of the sample means again. But in this case, we still have 500 sample means, but now each one is based on 50 observations. So let's look. The mean of the sample means is, again, 125 millimeters of mercury. And the sample standard deviation of these sample means is 1.9 millimeters of mercury, lesser than it was when the means were based on 20 observations each. So we still have time. We're getting excited, so we decide to do one more experiment. What we're going to do is the same thing ostensibly, but now each of the samples we take will have 100 subjects randomly selected. So for each of the 500 samples of 100 men, we will again plot a histogram of the sample blood pressure values, record the sample mean, sample standard deviation, and then look at them collectively. We'll see two more samples here, each of size 100, and we're getting a little more information visually, and they tend to start really exhibiting evidence of symmetry and bell-shapedness, albeit a little bit crudely. And we've got our sample means and standard deviations for both samples here. So onward to the next step, where after having done those 500 samples, we'll now chart the distribution of the 500 sample means. So again, we have a histogram here of 500 sample means, and this time each mean is based on 100 observations. Well, let's look at this here. Well, the mean of these sample means is 125 millimeters of mercury, again. And the sample standard deviation of these 500 sample means is 1.4 millimeters of mercury, which is lesser than in either of the previous two distributions of sample means based on lesser numbers in the samples. So let me just summarize that information about the distribution of sample means across the three sets of studies. So looking at studies based on 20, 50, and 100 persons at a time respectively, and comparing this to the population level characteristics. Well, the true mean at the population from which we sampled was 125 millimeters of mercury. Look at the results from these 500 random samples. In each case, the mean of the 500 sample means was 125 millimeters of mercury, whether our samples were based on 20 men each, 50 men, or 100. So what does that say? What does that start to point at? Well, it starts to suggest that the average of sample means across multiple random samples of similar size from a population, the average of those sample means should be the true mean. And then we see the standard deviation of those 500 sample means was decreasing the more information each mean was based upon. So the spread in the 500 sample means was lesser when each mean was based on 100 than it was when each mean was based on 50 observations, which in turn was lesser than when each mean was based on 20. And then the shape of the distribution of the 500 sample means in all three cases was approximately normal. And here's a box plot presentation of the three distributions side by side, where you can see as the amount of information each mean based on increases from 20 to 100, you see our distributions getting tighter there. Okay, let's do this again, but with a different starting population. Recall we had worked with data on hospital length of stay using a random sample of 500 patients taken from a sample of all patients discharged in the year 2005. Let's assume that the population distribution, the true distribution that gave birth to this data, is given by this picture here, where the true mean length of stay is 5 days and the true standard deviation is 6.9 days. And here's a box plot presentation that really shows how skewed that distribution of data points is in the population. So again, suppose we had all the time in the world. Again, I don't know how we keep getting this, but as long as we've given it to us, let's go for it. So we decide to do another experiment. We are going to take 500 separate random samples from the population of patients, each with 20 subjects in them. And then for each of the 500 samples, we will plot a histogram of the sample length of stay values, record the sample mean, and sample standard deviation. And we're off. Well, here's the first sample. And what I've done is superimposed a normal curve over it with same mean and standard deviation of the sample. And you can see very clearly that the sample distribution does mimic the right skewedness of its population counterpart, which it should, and is not well described by a normal curve at all. The sample mean is 6.6 days, and the sample standard deviation is 9.5 days. And similarly, the second sample also demonstrates that heavy positive skew, and the superimposed normal curve only covers part of it because this data is not well described by a normal curve. And the sample mean length of stay is 4.8 days, and the sample standard deviation is 4.2. So again, we go through this process 500 times, and we get 500 means, 500 sample means. And now I'm going to plot a histogram of those 500 sample means. Look at this. This is sort of interesting. I've superimposed a normal curve on top of this distribution of 500 sample means. And while I wouldn't claim that this distribution is perfectly well described by a normal curve, it certainly looks more normal-esque than the distribution of individual values in any of those samples we looked at before. The mean of these sample means is 5.05 days, and the standard deviation of these sample means is about 1.5 days. So again, all the time in the world, so we're starting to, curiosity is getting piqued. Let's try this again. What we're going to do now is we're going to take 500 separate random samples from the population of length of stay values, each with 50 observations. And for each of the 500 samples, we will plot a histogram of the length of stay values and record the same thing we've been doing over and over. So let's do this. This is our first sample based on 50 observations. You can see it, again, captures the right skew of the values. Sample mean is 3.3 days, sample standard deviation 3.1 days, and similarly the second sample has that right skew as well. Now let's look at a histogram of the 500 sample means. Now look at this. It's starting to show some evidence of symmetry and bell-shapedness, despite the fact that the individual level on data in any of our samples mimics that right skew in the population that we saw. When we start looking at the behavior of summary measures based on 50 pieces of information each, it starts to look more symmetric and bell-shaped. And here, the mean of these sample means is 5.04 days, and the standard deviation is 1 day, which is lesser than the standard deviations of the sample means based on 20 observations in each. So let's just do this one more time, so that we totally mimic what we did with the blood pressure measurements. And now we'll take 500 samples, each with 100 patients in them, and do the same thing. So let's look at the results of two samples. Here's two samples side by side. can see they both have right skewed distributions of the sample values, and I give their means and respective SDs below. So let's just jump right to the chase and look at the histogram of the 500 sample means, each based on 100 observations. Look at this. Wow. Now we're starting to see some real evidence of symmetry and bell-shapedness once again. And the mean of our sample means is similar to the mean of the sample means from the other simulations, 5.08 days. But the spread, the standard deviation, is the smallest amongst all three sets of sample means, coming in at about 0.78 days. So let's just review the results and remind ourselves of what's going on here. Remember, the population distribution was centered at 5.05 days and the standard deviation 6.9 days. The results from these random samples, we see that the means of the 500 sample means in all three sets of studies, whether each of the means was based on 20 observations, 50, or 100, is very close to that true population mean of 5.05 days. And despite the fact that the individual values in the population were heavily positively skewed, and hence when we looked at any single sample from the population, the sample values were heavily right skewed. If we look at the shape of the distribution of the 500 sample means, it was approximately normal in all three sets of simulations there. And here's just another take at it, looking at side-by-side box plots of the distribution of the 500 sample means for each set of sample sizes they were based on. And you can see, going from samples based on 20 to 100, we again see the distributions getting thinner, less variability. But all three, they all have some minor positive skew to them, but for the most part are symmetric, and certainly more so than the original length of stay values at the individual level. What do we see across these two examples, the blood pressure of men and the length of stay for teaching hospital patients? Well, we saw a couple of trends. The distribution of sample means tended to be approximately normal, even when the original individual day was not, which was the case for length of stay. The variability in the sample mean values decreased as the size of the sample each mean was based upon increased. So the more information that went into each of the means, the less variation there is in those sample mean values. And the distribution of sample means, regardless of sample size, tended to be centered at the true underlying population mean from which the samples were taken. Just one thing to be clear about, I'm not going to rehash and go through more simulations in the same detail, but the variation in the sample mean values is high. This was a simulation exercise where I arbitrarily took 500 samples at a time. But the variation in the sample mean values is tied to the size of each sample selected, not to the number of samples. And just to illustrate this, I actually redid the same simulations but took 5,000 samples at a time. So I did that for the blood pressure example, and I took 5,000 samples of 20, 5,000 samples of 50, 5,000 samples of 100. And what I've done on this picture here is I plotted the distribution of the sample means from those 5,000 samples compared to the 500 samples for each sample size setup. And you can see that while the distributions aren't perfectly the same, the spread, the center, etc. are similar. So if you look at those first two box plots, they show respectively the distribution of 500 sample means from 500 random samples of size 20 next to 5,000 sample means from 5,000 random samples size 20. And the shape and center are not markedly different. However, if I look to the right at those two box plots to describe the behavior of 500 and 5,000 respectively sample means based on samples of size 50, those two box plots, while similar to each other, are much narrower than the two box plots describing the distribution of data based on samples of size 20. So the point here is this is just a simulation exercise. The thing that's fueling the spread of those sample means is not the number of samples I take in the exercise, but the size of the information each sample is based on. So the more information that goes into each sample, the more information goes into each sample mean, and the tighter the variability is in those sample means.